So it's going to be me for the next 2 hours. So I'm going to bore you a lot. So my name is Rishabh. I'm a research scientist based in London, working for Spotify Research. I've been there for like just over 12 months. I joined last year. And so basically, this talk is going to be about some of the work we have currently in production at Spotify, specifically on the homepage, some of the other research work we have been doing for the past 6 to 9 months. It just disappeared. So in the first part of the talk, I'm just going to be mentioning about marketplaces, giving a brief tinge of like insights around what marketplaces are and why we should think differently about them, but mostly focusing on this Rexis paper we had earlier this year on explore, exploit, and explain, trying to work with explainable recommendations in a bandit, contextual bandit setting. And then in the next part of the talk is a bit more mathematical, going into the details of multi-objective models which are needed for marketplaces. So in the second part of the talk, I'll be focusing more on some trade-off analysis, a lot of these multi-objective machine learning models, specifically around marketplaces and cater to Spotify as such. So a quick question, how many of you are using Spotify? Cool, and how many of you aren't? Wow, that's a handful. So in general, I don't know why this is here. What's this Google Scholar button? Cool, went away. So basically, so Spotify is a music streaming app. We have over 100 million paid subscribers. We have over 150 million total users. Most of them are monthly active users. I'm not sure if the number I know I'm allowed to publicly speak, but yeah, we're doing decently well. So in general, this work is around some of these topics. So if you're remotely interested in any of these, like marketplaces, bandits, multi-objective, relevance, satisfaction, fairness, so if you're what related in these, then you might want to stick around for the talk second as well. If you're not interested in these, then hopefully, if you stick around by talk 2, then I should be able to convince you why these are important topics. Before deep diving further, just a brief view about myself. I was at UCL until last year working on machine learning information retrieval. Before that, I was visiting, during my PhD time, I was visiting Microsoft Research. I started a company, usercontext.ai. Nothing happened. Dumped it after 6 months. Came back to a paying job. Then before that, I was at BITS Pilani back in India doing my undergrad in computer science and mathematics. But more importantly, the kind of research areas I've worked on recently is machine learning for marketplaces, including some of the papers I'm going to talk about today. My PhD thesis was on search task and user needs, trying to understand why a user is using a search engine and what kind of tasks they have when they use any digital service as such. I've done some work on conversational agents, working with Cortana, a lot of the data, and a lot of these papers are from my Microsoft research internships, and I've worked with few people who are here in the audience as well. Some of the other work on user modeling personalization, something which, if I had to redo my PhD, I would pick up counterfactuals and causal analysis, because this is like a very lovely topic which I absolutely love as of today. So in general, we start with like traditional recommendation approaches. So what I'm going to do is, in the first 10, 15 minutes, just give you a flavor of what kind of research has happened in the academic literature. I'm sure a lot of you are already applying these and doing fancier things in production, but this is just a brief summary of what traditional recommendation system approaches look like. So people started with matrix factorization, collaborative filtering, and just kind of creating a matrix of users and items, ratings. You decompose them into 2 matrices and then use them as features to do some relevance, scoring, ranking, and recommendation as such. Then in 2010, there was this AAAI paper around extending matrices to tensors. So in the Netflix challenge, people found out that the matrix factorization is very helpful. So they extended matrices to tensors. So tensor is nothing but like a 3-mode or 4-mode matrix, just an extended form of matrices. And then once you have a tensor, then you can add a lot of metadata information, like users, location, and activities. That could be a tensor. We did some work around user, topic, task. Then that could be a tensor as well. So basically, you can enrich the matrices with additional side information, and then do some fancy join with a matrix and a tensor decomposition. So you can put in a lot of metadata, extend it into tensors, and then decompose them and get some good results. There's been a lot of work on latent variable models. So like David Blee, back in 2003, introduced this LDA paper, which served as the holy grail for a lot of PhD students to publish a lot of follow-up papers and complete their PhDs over the next 15 years or so. So latent variable models, I mean, this is just to scare you that there's a lot of work around there. But the core idea is that if you have an intuition, then latent variable model allows us to encode that intuition in a graphical model, which you can define probabilistically, define these distributions, and then do inference. So a lot of work has gone into these latent variable models. They perform very nicely up until the deep learning era came through. They have some scalability issues, but I'm aware of quite a few of these are currently in like large-scale production systems in a lot of major companies. So there is a lot of promise around that. One of the good papers I liked was the Rexis 2015 paper, which is using this probabilistic model for item recommendation as such. Then embeddings happened. Back in 2012, 2013, there was this nice seminal paper on Word2Vec, which was a skipgram model for learning embeddings. Now, once you have a model to learn embeddings, you can learn embeddings for users, you can learn embeddings for items. What you can also do is, there's this paper at Rexis 2016, wherein the product embeddings were enriched using site information. So basically, you add site information to your original metrics, to your original information, and then learn these embeddings together. What you can also do is, there's a wisdom paper back in last year, 2017, which was doing a much better, like a richer, sophisticated job at jointly modeling the users and items. So basically what you have is, you have the user review text, you have the item review text, and then you can have like some parallel network and jointly train them using a common loss function. So this was one of the nice papers back in last year at Wisdom. So again, the idea is like a lot of work has gone into developing these neural embedding models using some fancy architectures. And a lot of these upcoming ones are generative adversarial network models, which can also give you a lot of good representations. There's this nice paper at dub last year on neural collaborative filtering. So far we have seen that we can learn these, using matrix factorization, I can learn what collaborative filtering allows us to kind of gain from. So the idea is like collaborative filtering tells you basically that if this user is interested in something, then similar users would be interested in something similar. And we've seen like neural embeddings and these deep learning approaches are pretty good at kind of extracting these deep nonlinear relationships. So this paper was one of the first to combine neural models with collaborative ranking. So basically you have the user and item latent vectors, and then you kind of have this neural collaborative filtering layer, which jointly train the cross embeddings between user and items, and then you can kind of train using some loss functions and finally predict the score or the rating. So this was a nice combination of the two advantages, like a collaborative filtering approach and a neural representation learning approach. Now there are a lot of these are some of the models which people have used to learn representations for recommendation. But when you're doing recommendation systems, a lot of times, a lot of these different problems come in. One of them is like short-term versus long-term, that the user's interests change over time. In some domains, it's more common than others. So there was this paper back in CIKM 2012 on modeling the impact of short-term and long-term behavior. So like the idea over here is that if the user is at this point of time, then I can use some session, the current session representation or current session information to personalize. Or if the session is something not very useful, then I can fall back on historic information. So how do you trade these off? Till what extent do you go back to create your representations? This paper was like a nice overview around that. The other problem is cold start and cohort base. This nice paper in CIKM 2014. So cohort is just like a fancy name to say groups. So in general, you can divide users into groups, clusters of users, groups of users, and then do some representation learning or personalization. This paper is specifically for search. What you can also do is like you can have like multi-view and multi-interest models. So basically, if you have a user and like an item can have multiple views. You can have images, you can have metadata, you can have reviews about that. So once you have this multi-view information about an item, what you can do is you can have this Siamese network kind of thing wherein you have different views, or if you have different interests of the users, then you can have some parallel architectures for each of these and then jointly train them to learn your representations for recommendation. This is KDD paper from earlier this year, which is one of the very nice papers I came across, which is on multitask recommendation. So this is also kind of coming up. Like people are trying to train ambitious, deep architectures which perform n different tasks, and then they're kind of generalizable enough to perform good on new tasks as well. So the idea over here is that you jointly train a model for each of the tasks you care about. So a lot of recent work at ACL in a lot of these NLP tasks have shown that if you do a multitask network, then it's kind of better performing than a lot of single task networks. And the idea over here is that you can learn additional information from the other task, which helps you do better on one of the other tasks. So this is a nice paper which I recommend if you're interested into multitask work around recommendations. So as such, there's a lot of work here on a lot of different topics using a lot of different models. But what's the commonality over here? The commonality is that they're all user-centric. That everybody over here talks about just the user representation, the user representation, user models, user engagement. And in general, traditionally, and so far, a lot of work, majority of work in recommendation systems has been user-centric. They create models catered to user needs, they capture user interest, look at user behavior, user interactions, try to have personalized models, and the evaluation is also focused on users, like measuring user engagement, optimization for user satisfaction, a lot of these user-centric methods. So it's always focused on the user. And if you're interested in some of these, like a nice tutorial at Wisdom earlier this year, the moment I move my mouse, this goes away. So there's a tutorial behind this, which is a nice overview on some of the metrics on user engagement. And this is a Wisdom 28 tutorial. Munia is my manager, so she's at Spotify Research. She was at Yahoo Research before. So it's a nice disclaimer around that as well. So in general, so a lot of work has been around user-centric systems. But the moment you go to some of these new and upcoming super cool companies, like Spotify, like Airbnb, eBay, a lot of these companies are marketplaces. Now, what exactly is a marketplace? A marketplace is an intermediary which helps interaction between two or more sites. So if you go to Uber, so you not only have users like me who use Uber, you also have drivers. So if you go to Airbnb, then people like me want to live in an Airbnb, but then you have to have host. On Spotify, we have the users who want to listen to music, but you have artists who should create music for you. If you're on, let's say Amazon, e-commerce is a very typical example. I won't go to Amazon if the retailers are not selling products on Amazon. So typically and importantly, the success of a marketplace depends on both the sites flourishing. And by both the sites, I mean consumers and suppliers both. So usually when you talk about like these user-centric recommendation systems, then most of them have focused on consumers because users consume. But in a marketplace, if you don't care about suppliers, then you're not going to have a flourishing marketplace as such. So a lot of new research and a lot of very good companies, a lot of IPOs in 2018, 2019, and 2020, they're going to be around these marketplace companies. And so it kind of throws up quite a few interesting challenges, which we are going to consider today and look at some of them. So Spotify as such, I mean, we've mentioned in our SEC filing for our IPO that we are a two-sided marketplace with the aim of kind of giving 1 million artists enough money so that they can live off from Spotify. But in general, the goal of the recommendation models for us would be to connect the artists and the fans. So Spotify is an example of a two-sided marketplace, wherein we want to connect the two sides in a way wherein both the sides flourish. So when you talk about two-sided marketplaces, then when you're designing these recommendation models, then you have to look at the different stakeholders. So far, traditionally, we only used to consider users. But in a marketplace like Spotify or others as well, you have different stakeholders like artists, advertisers, campaigns, or some promotional campaigns, and platform provider itself. So in general, a lot of these objectives come in from these different stakeholders. So when you're talking about these objectives and metrics which we want to maximize and optimize for, then for the users, we know like people should stream more, the engagement should be high, we should have like retention, we should have a lot of these other proxies of user satisfaction. This is a slide specifically around like Spotify needs. But in general, you want in your marketplace the user to be happy. And you do a lot of research around defining and designing metrics which measure whether the user is happy or not. So this is what the major focus has been so far. But the moment you kind of look at the other stakeholders now in this multi-stakeholder environment setting, then you have these exposure, audience growth, revenue, long-term value, diversity, and a lot of these algorithmic fairness, and some of these issues come in. And these are the objectives you want to kind of cater to. So just giving you an example that this is the homepage of Spotify, and each card is a playlist which we show to you. So in general, if I disregard the multi-sided, the multi-stakeholder aspect in a marketplace, then what I would do is I would have some, basically, if I have to pick up a playlist, then I'll just maximize a function which only depends on some user metric. That I only care about users, I only have a metric which quantifies the user satisfaction, so I try to maximize it and show you playlists which maximizes user satisfaction. But in general, user-centric machine learning models are not meant to optimize for different objectives. Like, what if I have competing objectives over here? What if like diversity is unrelated or competing to a user satisfaction metric? So the moment you have a multi-sided marketplace, then you have these objectives which might compete with each other. So this is an example wherein, like, in a typical marketplace, we could have like a user, we could have the artist, we could have labels, and we could have the platform provider itself. And instead of a single function over here, which says that optimize just pi, which is user-centric, ideally what you want is you want a function of the different objectives of the different stakeholders as such. So now a lot of research has gone into designing these metrics from the user to this to this model. But this is like a very relatively, like in the academic literature community, it's like relatively new that what are these metrics which these different stakeholders would care about. And in general, the moment we go from a single objective to a multi-objective world, the recommendation strategy becomes this, that instead of focusing on just a single objective, which is user-centric, you have a multi-objective model over here, which is taking into account metrics around users, artists, Spotify economics, and many other things. This is just like a demonstrative example. So how do we find these? So what is the recommendation? What is the playlist which would make sense to all of these stakeholders and not just users? So to do this, what we have to do is like we have to find recommendations which satisfy multiple objectives. So now this might give you a hint of looking at some Pareto optimality, like wherein you have two objectives. The solutions on this red line are Pareto optimal, so that you cannot do better than this. So in general, in the multi-objective optimization, like around 2 or 3 decades or more of work has been there, like multi-objective, multi-sided, multi-criteria, multi-attribute, multi-agent. A lot of this work has gone into developing these multi-objective optimization models. So we're going to discuss some of these today, but with this background, I just want to mention what this talk is going to be about. By this talk, I mean like this and the follow-up. So in the first phase, I'm going to start with showing what a user-centric recommendation system model might look like. So this is a model we have in production at Spotify, powering the homepage of Spotify for like 99% of the traffic. So this is a bandit model which takes into account the explore, exploit, and also explanations. So what I'm going to do is motivate from here and try to inject a competing objective. Like so far, we only care about serving recommendations which are relevant to the user. But what if I inject some fairness attribute, that I want to be fair to my artists as well? I care about my consumers, like my users, but I inject one single objective around my suppliers. So in the second part, we're going to talk about this CIKM paper we had earlier this year, which was trying to trade off relevance and fairness. But the coolest thing which I want to talk about is towards the end, which is this multi-stakeholder bandits. So this is where we're going to talk about some of the paper we have under review at AISTATS, which talks about like a multi-objective contextual bandit model. So this is the spectrum of today's talk. Hopefully by the next 15, 20 minutes, I'm going to cover this. We'll take a break and then come back and cover these two. Any questions so far? Cool. So that's the outline. We've talked about some introduction. Now we're going to talk about like explore, exploit, and explain using bandits. And in the next part, we're going to talk about some trade-off and some multi-objective bandits. So this work is, I mean, if you sleep for the next 20 minutes, and if you want to recap, then there is a Rexis paper which describes this work. The idea is that we present a model to kind of, so basically, the question we want to ask is, how do you explore, exploit over explainable content? So in general, how many of you are familiar with the idea of explore, exploit? Cool. For those who aren't, so what traditionally these bandit models do is, I think I might have a slide later. Yeah, so there's an octopus, which is pretty famous. So these multi-arm bandits terminology comes in from the bandits you have at the casinos. So the idea is that if I know that the user likes something, then I would kind of rather exploit and show that to him. But if I do not know whether the user would like some things or not, then I have a budget for exploration that 95% of the times I will exploit and show you things which I know you like. But 5% of the times I would go on an exploration mode, randomly pick up some things from things I do not know about you, and then show that to you. And then I'll observe my feedback. That if I show some random things to you, if you like it, then I'll update my model. If you do not like it, then I will also update my model. So basically, you can do this explore-exploit strategy to cover a lot of interest spaces of the users. So in general, if you look at the Spotify homepage, then we work with something called shelves and cards. So for us, and for the next 1.5 hours, a card is a playlist, which we recommend to you, and a shelf is this rectangular thing you see on the homepage of Spotify. Now, this problem is very similar to some of the problems Netflix and other companies are facing, because if you log on to Netflix, then you also see these like slates. So they have this paper, there was this nice paper on slate recommendation at NIPS last year, which is talking about how you do recommendations in a slate setting. So this is a version of multi-slates, that we have one slate over here, and then we have corresponding slates as you scroll down. So the question we want to ask is, how do you explore exploit over explainable content? So in general, what the traditional explore exploit means is that, I mean, this is something which I already mentioned, that if it is not relevant to you and we are highly certain it's not relevant, then we're just going to ignore it. If it is highly relevant and we know that it's highly relevant to you, then I'm going to exploit it. And in the other cases, if the model is not certain about whether you like it or not, whether it's relevant to you or not, then I'm going to explore. So this is the traditional explore exploit. And what do I mean by explainable content? By explainable, we mean these explanations which we show on the homepage. So this is the homepage which I had today morning at 9:22 when I started making these slides. And so the idea is that for each shelf, we offer an explanation on why we recommend this to you. So some of these playlists are like your top songs, your daily mixes, and Discover Weekly. These are playlists which Spotify personally creates for you. By personally, I mean these are personalized playlists. So this is made for X. In general, some of the other playlists we recommend based on your recently played history. So we recommend this because you recently played this. There's this other shelf, which is your heavy rotation. So this is the music you have kind of had on repeat this month. So what we do is we kind of have these explanations, which some of these examples from the small data set we sampled looks like because it's Friday. So I mean, it's like a Friday music, so we recommend you some songs. Inspired by your recent listening, because it's a new release, because you have liked rock music in the past, because it's popular, it's a mood, or it's a focus playlist, some of these. So this is an example of some of the explanations we have shown around our recommendations. And in general, if I want to know that which playlist should I recommend to you for each of these explanations, then it's intractable. Because naively, the bandit has to try every possible combination of a playlist and the explanation before it knows what you like or not. So before it can do this exploitation, it has to explore a lot, because the space just gets multiplied by the space of explanations there are. So this is a problem which we try to solve using this Bart model. So Bart is an acronym which James, the lead author on this paper, came up with. And I mean, people like referring to Bart and internally at Spotify as well. So BART actually means Bandits for Recommendations as Treatments. In general, it consists of three parts. The first part is a user preference model, that we try to learn your representations based on the context. The second part is a ranking procedure and a training procedure. So in general, the user preference model currently we have is a factorization machine, which captures interaction between features. So there's this paper by Rendley in 2010, which kind of details these factorization machines. So we tried a bunch of other approaches, and factorization machines gave us a lot of these like second order and third order interaction effects across features, which we wanted to capture. In general, the context could include anything we know about the user and the playlist, which includes the region, age group, recent listening activity, patterns, time of the day, and others. The training procedure is counterfactual maximum likelihood. So this is this nice paper from Thorsten Bjorkins and Adit Swaminathan, who were at Cornell at the point of time. Adit is at Microsoft Research now. So the idea over here is that we collect some random data and try to do this counterfactual training. I'm not going to go into details of this. In the next few slides, I'm going to focus on the ranking procedures used over here. A quick show of hands, how many of you are aware of counterfactuals, have heard about them before? Okay. So in general, what Bart does is it tries to explore, exploit, and explain. So the idea is that I have to select an action. So by an action, I mean I have this set of cards, set of playlists, which you might potentially listen to. From this space, I will select a playlist to show to the user. So the action is, which playlist should I pick? So for this action, what we do is we have this policy which takes into account the exploration strategy. So some of the work around Expal greedy, around Thompson sampling, that tells us how do we do the exploration. So epsilon greedy is a very simple model. It says that with probability 1 minus epsilon, you do exploration. With epsilon probability, you do exploitation, or vice versa, basically. So if the epsilon value is 5.5, then 95% of times you're going to exploit. Show user content which you know they're going to like. And with 5% times, you're going to explore and then show content which the model is uncertain about. You have this reward model, which tells you how likely is the user to like this card, this playlist. So you can have a factorization machine, you can have a regression model, which tries to predict that if I show this playlist to the user, then will he be happy or unhappy with that? M is a set of candidates, which is the set of playlists we want to pick. So in general, we want to be able to solve this problem that we want to devise a policy which tells us which card, which playlist to recommend to the user. So if you look at this homepage on Spotify, then we have this like, you can scroll horizontally and you can scroll vertically. So if you scroll horizontally, then this part of the app remains static, but we show you new cards over here. So new playlists come up as you scroll horizontally. If you scroll vertically, then new shelves come up, which is pretty intuitive. So in general, what we do is like we have this shelf browsing model, which is the horizontal scrolling and vertical scrolling. So what a horizontal scrolling might look like. So this is the screen which the user sees at any point of time. And we have this set of cards which are the candidate cards. So these are the playlists which we might show to the user. So what we do is this is going to be annoying. I'll wait for 10 seconds, yeah. So basically what we do is, from these sets of playlists, I pick up a playlist based on the policy. So this policy tries to say that will you like this card or not? So based on this policy, we pick up a card and then show it to the user. So this is the first card which gets populated at the top left. What happens next is that we have to pick the next card. Now we have removed card 1. In the new space of candidate cards, M2, we now pick up another card based on the same policy. We showed it to the user, and then we kind of go like so on and so forth. So basically, if I start creating a shelf, then I'll pick cards using my policy and then show it in the shelf in that particular order. So this is how a shelf is generated. Now I can do the same I can generate all the shelves for all the explanations. Now which shelf to rank is another bandit model over here. So let's say instead of candidate cards, I have candidate shelves. So now I've created, for each explanation, I've created one shelf. Now which shelf should I show at the top is this vertical scrolling problem. That I have this set of candidate shelves. I pick up one shelf based on a new policy, which is the shelf picking policy. The space of shelves is different than the space of cards. And then I show this shelf to the user. And because I've already created this shelf, so the new next card is also populated. I can do the same vertically and then keep on creating these new shelves. And I can do it like so on and so forth. So basically, this home page is populated in a hierarchical manner. I first decide what cards to show in a shelf, and then order these shelves. So there's like a 2-level model over here. We are doing this ordering of the cards in a shelf, and once we have these shelves, then we are doing this ordering of the shelves. So this is typically how the home page is populated. And philosophically, from published literature, it's something similar philosophically as to how Netflix shows you recommendations as well. So in general, when we do this, then we kind of did some offline and online A/B test experiments around this, and we got some pretty decent performance boost with the control model we had, with some logistic regression models, some randomly showing cards. But the interesting part about this is that we collected randomized data. So if you do not know counterfactuals, then do go back home and look it up. The idea about counterfactuals is that if I randomly show certain things to you, then that random data allows me to do a lot of good machine learning work, a lot of good evaluation, a lot of good training, which helps you kind of train your model in unbiased manner. So the idea is like, if I keep on showing you cards over here, and if I use this data to train the next model I generate, the problem is that the cards which do not come at the top, we have a lot of less data around those cards. So you have this bias, which is the position bias over here. So what you do is, if you randomly, for a small percentage of A/B test, if you randomly show playlists to the user, then you try to kind of get rid of this position bias. So randomization gives us a lot of theoretical guarantees, which we should kind of explore. So at Spotify, what we do is like we always have this flight, which is an A/B test, which we keep on collecting this randomized data to a certain segment of users. For certain sessions, we show them random cards, random playlists, and then log that. And we use that to evaluate offline, which is called the counterfactual evaluation. And we also use that to kind of counterfactually train our model as well. So we are writing up a paper around that. So in general, I mean, if you suffer from this position bias, then counterfactual training is very important for you. And counterfactual evaluation is also important because that kind of allows you to cut short on the A/B test. So in general, on the A/B test traffic, we found some good results. This is one of the very early results. And this was around last November or December. After that, we did some follow-up, and it gave really good boost. So we kind of rolled it out to 100% of the traffic. So if you go to Spotify homepage, this is a kind of model which is kind of powering your homepage right now. But in general, I mentioned this explanation stuff. So this is one of the other, I'm not mentioning a lot of results, but one of the other key results which we found out was, which is kind of intuitive, that explanations actually help in a recommendation setting. So what we did was we tried to do some null hypothesis testing, saying that the explanations have no effect on the user satisfaction. So if we reject this hypothesis, that would mean that users respond differently depending on what explanation is used. And this kind of motivates the need to do personalized explanations. So an example of that could be, oops, I have the same slide with a different title. So an example of that would be that if I pose my null hypothesis as the outcome of whether the explanation results in user streaming is independent of the choice of explanation. So what this says is that does the choice of explanation matter? That if I'm showing you this playlist, if I randomly remove this explanation and substitute something else, would it make a difference? So what we did was we did this testing, and in the offline evaluation, we were able to reject this hypothesis and using chi-square test. So basically, what it shows is that streaming behavior is dependent on the choices explanations. So for the same card, if you replace the explanation by something else, then the engagement metrics change. Another interesting thing is that if an explanation A has higher engagement than explanation B, like we know that recently played as a shelf is a lot more consumed than other shelves. Now, why is this happening? Is this happening because users respond better to A? So one cause could be that A is more intuitive to the user, they kind of understand it, so they click more. Or explanation A has more interesting playlist. So now we wanted to understand why this is happening. So what we did was we investigate whether there's like an intrinsic appeal to some shelves. Like, are some shelves intrinsically better at getting more user engagement than the others? So we posed this another null hypothesis around whether the outcome of whether a user streams is independent of the choice of explanations provided. So what we did was we divided the set of explanations into two sets. One is this set one, which is day of the week, inspired by your recent listening because you liked something or popular, and the other set was mood and focused. So these are the set of explanations we have, and we were able to reject this null hypothesis only for set one and not for set two. So what does it mean? It means that explaining a playlist based on different reasons makes a difference, which supports the previous hypothesis as well, that if for a playlist, if I show you one of these, then the user engagement actually changes. And in general, what we saw was that popularity was the weakest driver for engagement, and recent listening and genre-based explanations were the strongest. So, you have a question? Yeah.
Just a clarification. So, when you mean by explanation, you mean the whole shelf?
Yes.
Like the description and the data?
Yes.
You haven't tested whether you did, let's say, the same
So basically what you can do is, in the previous hypothesis, what we did was the shelf content remains the same. We switch the explanation. So, so that helps us disentangle, is this the card or is it the playlist that's making you engage, or is it the explanations? So that's covered in the previous one. Over here, what we're trying to do is like, across these, what happens when we switch? And over here, we see that in general, people don't usually consider popular playlist as a motivation, which is kind of counterintuitive because, I mean, I don't trust my music taste as much, so I'll rather rely, I mean, it depends on the users as well. So some users might not trust their, I should have talked about this in third person. But in general, yeah, I mean, so we saw a trend that popularity is not the strongest, but recent listening and genre-based recommendations are more kind of strong indicators for user engagement. Interestingly, because we were able to reject this hypothesis for set 2, it could have like 2 explanations. One could be that mood and focus are vague explanations. I mean, if I'm telling you that it's this playlist is recommended because you recently listened to it or because it's related to your taste, then that's like more stronger than just focus and mood. Yep. Yeah, so we don't measure these. So basically the idea is that, so there is a separate work which says that some of these playlists are meant to be focus oriented. So when the editors create a playlist, they tag a playlist with the need or the objective. So we have these tags for each playlist. And some of these tags are like for focus, like you're working and you have like, you want to kind of focus, so it's like instrumentals playing, which makes you focus. So it's like some domain specific models. There's also some work internally around automated tagging of these. So right now we're agnostic to it. All we get is like this playlist has this tag. So basically these explanations are also weaker calls to action. So that may also be a reason why this kind of fails the hypothesis test here. So in general, what this shows is that explanations do help, which is kind of intuitive as well, but it was nice to see it experimentally on a very large scale test as well. So what we land up with over here is that right now there are a lot of limitations and a lot of current work which we have been doing, which is not public for confidentiality issues. But in general, the model we have described so far assumes there's an independence of impressions. So right now, if you interact with the card at the top, that's independent for the interaction with card at the bottom. So in general, search as such progress from individual. So if you imagine a search result page, then if you go to Google or Bing.com, then you have the query, you have a list of results, you have the Wikipedia panel on the right, you have some news answers, you have some images, you have some related searches. So the way search evolved was that initially they started optimizing only for the individual components, that what are the best results to show, what are the best blue links to show to you. And eventually they moved to whole page optimization, that what does the whole page look like to you? So instead of just optimizing for related searches separately, for news answers separately, we optimize them together. So this is where we should kind of maybe go towards like whole page optimization of cards to you. There's also this, we rely on this reward function because the bandit models heavily relies on reward. So we have this work which is submitted at dub.org, which talks about more fancier ways of defining reward. A simple reward could be that if you stream from a playlist for more than X number of seconds, then we think you like it. So that's like a +1. If you don't stream, then that's like a 0. So that's a very simple model of reward you can work with. You can also do some fancy machine learning around reward modeling. But the key point over here is that because we are trying to optimize for the reward, then does your reward actually approximate user satisfaction? That, I mean, I can construct my own mathematical function of what the reward should be, but is it actually correlated with user satisfaction at all or not? So that's a very important question which needs like thorough investigation. In general, the ranking over here is not defined to promote diversity or any of the other constituents. The work over here so far only focuses on showing users something which we think they would stream. So this is like a very hardcore user-centric model and not fit for marketplace kind of work. And in general, right now, in production, we have this exploitation over a candidate set. So, I mean, there are like 1 million playlists as such on Spotify. And we are not doing it on 1 million playlist data. What we're doing is for each user, we have a set of candidate playlists which we select beforehand, and then we're running this bandit model on top of that. So we're trying to get rid of this assumption, but it's like a very hard problem to solve in a scalable fashion. In general, the last slide on this is, do you need bandits? I mean, if I'm working on a recommendation model, then should I consider bandits as a solution? So the things which we think you should consider are confounding. One is that, are you training a model using data collected with another model? So let's say you have SVM or logistic regression model in production right now. So you have a model which is a regression model, and you collect your data from that. And if you create a training data from that model and try to test a bandit approach, then there's like a very big red flag. Then forget about explore exploit. You should consider counterfactual evaluation, because the training data you're constructing from the previous model is heavily biased. So you should not idly use that training data to kind of evaluate a new model. So instead of focusing on bandits, we would advise you to consider counterfactual evaluation, which would be very helpful on its own. The other thing could happen is that is the aspect of auto-confounding, wherein you're repeatedly training a model using data generated from the same model. So I have a bandit model in production right now, and it's working in a way. And I expose it to 90% of traffic, I get the data, I use this to train the next version of my bandit model. So over here, the idea is to consider this exploration-exploitation in a better way than counterfactual. So if you kind of focus on this auto-confounding issue, then we would suggest that you should consider this bandit-based recommendations in your recommendation setting. So that's the summary. We've talked about marketplaces. We've kind of taken a detour and focused on one of the aspects of bandits for user-centric recommendations. And in general, we've seen some results around explanations helping in increasing engagement. In the next talk, we're going to talk about some more concrete examples of what this multi-objective model might look like. So right now, we have a single objective model which says that I want to optimize user satisfaction. But now, how do we make it multi-objective? How do we kind of do some trade-off between competing objectives? That's in the next part. And I have some motivation for you to stay for talk 2. Some of this would be some of this super fancy math, which we're not going to go through if it scares you. Some algorithmic designs, and some nice fancy plots, which my intern spent a lot of time plotting. And if you disappear after this talk, then a couple of things we should take into account. We had this Rexis challenge in 2018, earlier this year, wherein we released this data set of 1 million user-created playlists and a lot of metadata around these playlists. And the challenge was to predict tracks that would complete a given playlist. So it's like a playlist completion track. It could also be cast as a generic set completion task in a traditional machine learning framework. So we have this data publicly available, and we kind of got a lot of very good responses and a lot of good papers and open source contributions around this from the community, a lot of good work around basic nearest neighbor random walks to multi-stage ensembles. The winning approach was a multi-stage ensemble from University of Toronto in Canada. So, I mean, you might want to look this up. The other thing is we have this Wisdom Cup 2019, which is going to happen next year. And this is the first time anybody is releasing user interaction data in a session level. So I did my PhD on search, and I know that search people mostly rely on this publicly available controversial AOL logs, which got a lot of people fired. And I mean, so basically the idea is like, what we've done is we have looked at user sessions, not just user interactions in an item user way, but we're kind of releasing this 130 million listening sessions along with interactions. So we have interaction like, did you skip or not? How long after playing the song did you skip? And this is over a session. And for each track, we have a lot of metadata, a lot of user characteristics. And the challenge is to predict which track would be skipped. But this is just one of the challenges we can work on. But this data is like very, very powerful. And hopefully a lot of future research around session level modeling would benefit from this. So the submissions are still open, and this is a website for this. So yeah, hopefully I'll see you again in some time.
Time for a couple of questions. You got a mic and seat in front of you. Put up your hand.
Yep.
It's a simple question, really. How do you actually create a recommendation for a cold start? So I don't have a Spotify account. I log on if all you're showing me is Eminem, I'll never come back. So how do you actually make something clever?
Yeah, so that's an interesting problem, which is a very common problem, and it's still unsolved in like majority of cases. So the idea is like what you can do is you can do this cohort-based modeling. So initially I mentioned like some user groups. So at the minimum, what you could do is we did that for Brazil market. We are doing that for India as well. We're launching in India later this next year, and we don't have any Indian users in India using Spotify right now. I mean, legally, a lot of people are using it illegally. So basically, in a cold start setting, what you can do is like you can backtrack to the nearest groups which is similar. So like people geographically also behave differently. So like we have like Spotify launched in 78 markets. So a model for Belgium would be very different from a model for the US. So if you don't have anything about the user, you can start with looking at their demographic information, like their location, their geography. I mean, you can use the IP address and localize to a city and other stuff, but you can also do a lot of user traits, like you have the gender, you have the age group. So initially people used to log into Spotify using Facebook, so we have a lot of that data which we are not using right now. But if you have that access, yeah, we're not using officially. I would love to use that data because that's such a rich data to do research on, but then we're not, like, we're bounded by a lot of contracts. And yeah, that's not a research which I would want to do and get fired for that. So basically, but then you can fall back upon quite a few known traits about the user, not exactly for the user, but yeah. But also the other thing is like, there is a stages of cold start. Like you have zero interaction is something, but then like few sessions is something else. So even if you have 2 or 4 sessions about the user, then this bandit model allows you to kind of learn quickly from the feedback. So we are kind of doing some nice research around, and I forgot to say. I hope none of you are calling me to ask questions. So basically, the idea is like users' behavior changes rapidly over the first 2 weeks of interaction. Because if I'm a new user, then I start discovering what the app could do for me. And this is very true for Cortana and other digital assistants too, because when I started using Cortana, I didn't know it could solve these problems. So users learn about the app as well, and the app learns about the user. So there's a lot of exciting research possible to model the first few sessions of the users and how users evolve and how their thinking about the app evolves as well. So that's something which we are currently investigating.
Do you use any data or research from last attempt?
To my knowledge, I'm not aware of any, but I've been around for 13 months and I'm not working closely with all the engineering teams. I'm mostly working with the home team, and home doesn't use any last FM data. But yeah, as such, I don't know. Yep.
Can you hear me?
Yes, I'm not sure if others can, so it would be useful if you use a mic.
So you mentioned the reward system.
It's not useful.
Yeah, that's quite different. So you mentioned the reward model as well. So you have some machine learning techniques to actually capture what the user interaction and to figure out, well, do they actually like this recommendation? Now with Spotify, I imagine it's quite straightforward. They listen to the song, they like it. But what if you had something a bit more subtle, like, I don't know, in ResearchGate, you have like academic papers. So they're not buying it. They might not necessarily be printing it, but what kind of things would you be looking for to figure out whether that paper is actually of interest to them?
Yeah, so
I
know
it's an unfair question, but
no,
if
it
you
is a
have an
very
answer,
fair
that'd be
question, and
awesome.
it's great you brought it up. It's not simple in Spotify case. I spent like the first 4 months at Spotify trying to figure out these models. So you mentioned that it's trivial for Spotify if the user listens to a song, and then it's not. The reason why it's not is because we show you on an average, it's a ballpark number, we show you like 10,000 tracks to you. You interact with like 2 tracks, or you interact with like 5 tracks. So if you're creating a data set, then it's like 2 versus 98,000, and that's like not good. Same for playlist. So we show you like around 100 playlists in the home, and you just interact with one just because it was shown at the top. So so the thing is like a lot of work has gone around like implicit signals of interaction. And by implicit, I mean search. This is one of the work I did with Microsoft here in London as well. And Nicole over there would kind of testify to that. So a lot of work would be around like, let's say reformulation. In search, an example would be that if I issue a query, you show me the results. If I click on the result, if I quickly came back, then if I came back within 5 seconds, then you know that the user was not happy. If you stayed on the document and read it for like 20 seconds or 30 seconds, then you know that actually the reader actually consumed something. So this quick back is an implicit signal which we can use. If you reformulate the query in the next 2 minutes, that means the first results we showed to you were not good enough. So that's why you had to reformulate your query and issue a modified query. So these are some signals which search uses. On Spotify, these interaction signals are even more important because if you're scrolling, then a scroll as a signal is ambiguous. Because if I want to consider 2 cases, one is I want to kind of explore and find new music. So then scrolling is very good because the user is finding more, he's interacting more. But then if you're driving in your car and you're scrolling, then that's like life-threatening. So a scroll as an interaction signal is not very informative without the context. So we have this paper at www under review right now, basically saying that to predict satisfaction, you have to condition on the intent. And each signal, the interpretation of a signal is dependent on the intent the user has. If you want to find music quickly, or if you're driving in a car and just want to play something in the background, then the interpretation of these interaction signals is different. But if you're doing something else, then it's different. For the specific case, finally coming to your last question on the specific case of like reading papers, then, I mean, it depends on the instrumentation you have. So when I was at Microsoft during my internships, Microsoft has like a super cool box model, they call it, wherein you can log every freaking thing you do. So you can literally replay the entire user interaction journey, cursor by cursor, X, Y, Z. Z is time, X, Y on the screen, and with time, you can literally replay the entire sessions, and they kind of open source, they kind of release it to the public like 2 weeks ago or something. So the idea is like if you have that much amount of interaction data about people reading your papers, then you can see if they're scrolling, if they're kind of finding out some results, if they're selecting something, or if they're kind of copy-pasting something, then at least they found something useful. If they're just going back within 5 seconds, then that means you're kind of literally not showing anything useful. So it depends on the instrumentation you have. You can extract a lot of good interaction signals around that.
Cool. I think we should break here. So just